Welcome, everyone. Today, we're diving into LeetCode problem number 2210, count hills and valleys in an array. In this session, we'll explore how to identify and count hills and valleys in a given array. This problem is a fantastic opportunity to sharpen your skills in array traversal and problem solving. Let's get started. In this problem, we are tasked with identifying and counting specific patterns within a zero-indexed array of integers, referred to as hills and valleys. A hill occurs at an index if the value at that index is strictly greater than its immediate neighbors on both sides. Similarly, a valley occurs if the value at an index is strictly less than its immediate neighbors on both sides. It's important to note that these comparisons must be strict, meaning we ignore cases where the adjacent elements are equal to the current element. Additionally, if an index does not have both a left and a right neighbor, such as the first or last element in the array, it cannot be considered a hill or valley. Our goal is to return the total number of hills and valleys in the array. Let's look at an example to clarify. Consider the array nums equals 2, 4, 1, 1, 6, 5. The output for this input is 2. Here's why. Index 1 is a hill because the value at this position, 4, is greater than both its neighbors, 2 on the left and 1 on the right. Next, index 4 is a valley because the value at this position, 6, is less than both its neighbors, 1 on the left and 5 on the right. On the other hand, indices 2 and 3 are not hills or valleys because the adjacent elements are not strictly greater or less. For instance, at index 3, the neighbors are both equal to 1. Summing up the valid hills and valleys, we get a total of 2. Now consider a different example, where nums equals 6, 6, 5, 5, 4, 1. The output here is 0 because no hills or valleys exist. For any index in this array, the adjacent values are either equal to or not strictly greater or less than the current value. This eliminates the possibility of forming any hills or valleys. For instance, at index 2, the values 6 and 5 are not strictly greater than the current value, 5. Similarly, at index 4, the values 5 and 1 do not satisfy the condition for forming a hill or a valley. As a result, the total count remains 0. Finally, let's look at another example where the array is strictly increasing, such as nums equals 1, 2, 3, 4, 5. Here, the output is also 0 because no hills or valleys exist in a strictly increasing sequence. A hill requires the current value to be greater than both its neighbors, and a valley requires it to be less than both its neighbors. However, in a strictly increasing sequence, each value is smaller than the next, meaning the conditions for forming hills or valleys are never satisfied. In conclusion, arrays with flat segments, boundary elements, or strictly increasing or decreasing sequences will often result in no hills or valleys. It's also worth noting that arrays with fewer than 3 elements or arrays where all elements are equal cannot contain any hills or valleys either. To solve the problem of counting hills and valleys in an array, we start by understanding the definitions of a hill and a valley. A hill occurs at index I when the value at nums, I, is greater than its immediate neighbors, nums, I1, and nums, I plus 1. Similarly, a valley is identified at index I when the value at nums, I, is smaller than its immediate neighbors. Now, the brute force approach provides a straightforward way to solve this. We iterate through the array, skipping the first and last elements, as they can't form hills or valleys. At each step, we check if the current element satisfies the hill or valley condition using simple comparisons. While this approach runs in linear time, with a complexity of O(n), it struggles with scenarios where there are adjacent duplicates, such as 2, 2, 2, 3, 2, 2. These duplicates can lead to incorrect results because they invalidate transitions that are critical for identifying hills and valleys. Addressing this limitation is essential for ensuring correctness, and that's where an optimized strategy comes into play. The optimized approach builds upon the brute force method by introducing a pre-processing step to handle duplicates. The idea is to first create a new array where consecutive duplicate values are skipped, leaving only unique transitions. For example, the array 2, 2, 2, 3, 2, 2 is transformed into 2, 3, 2. This pre-processing ensures that the conditions for hills and valleys are checked only when there's a meaningful change in the sequence. After pre-processing, we iterate through the filtered array, examining each element from the second to last. At each index, we check if the hill condition, where nums, I1, nums, I plus 1, or the valley condition, where nums I1, nums I plus 1 holds true. Each time we find a hill or a valley, we increment our counter. This approach retains the overall time complexity of O(n), since pre-processing and the subsequent iteration both operate in linear time. While pre-processing adds a small overhead, it ensures correctness and simplifies the implementation, making this strategy both efficient and robust. Another method we could consider is the sliding window approach. Here, we use a window of size 3 to check the hill or valley condition at each step as the window slides through the array. While this method also has a time complexity of O(n), it doesn't handle duplicates as effectively as the optimized approach with pre-processing. When duplicates exist, the sliding window method struggles to identify unique transitions, leading to incorrect results or unnecessary checks. For this reason, the optimized approach with pre-processing is clearly the better choice. By focusing on unique transitions and eliminating duplicates beforehand, it ensures that hills and valleys are identified accurately while maintaining simplicity in the implementation. The small pre-processing overhead is a worthwhile trade-off for ensuring correctness and avoiding redundant calculations. This makes the optimized approach the most reliable and efficient solution for counting hills and valleys, especially when working with larger arrays. In this problem, we are tasked with counting the number of hills and valleys in an integer array called nums. A hill is a peak in the array where the value at index I is greater than both its neighbors, and a valley is a dip where the value at index I is less than both its neighbors. For example, in the array 2, 3, 1, the value 3 forms a hill and the value 1 forms a valley. However, consecutive duplicate values, such as 2, 2, 3, 3, 1, 1, are considered flat ground and don't contribute to hills or valleys. This means we first need to pre-process the array to remove these duplicates while preserving the order, reducing it to 2, 3, 1. Once we have this cleaned up array, our next step is to iterate through it, starting from the second element and ending at the second to last element, as we need both a previous and next value to evaluate hills and valleys. Now, at each index during the iteration, we check two specific conditions. First, if the current value is greater than both its previous and next values, it forms a hill, so we increment a hill_count variable. Second, if the current value is less than both its previous and next values, it forms a valley, so we increment a valley_count variable. These two counters allow us to track the number of hills and valleys separately. After completing the iteration, we simply return the sum of hill_count and valley_count as the total number of hills and valleys in the array. To better understand the need for preprocessing, consider that consecutive duplicates, such as 3, 3, 3, do not contribute to meaningful transitions in the terrain. Removing these duplicates simplifies our comparisons and ensures we focus only on distinct changes in the array. Additionally, we must handle edge cases where the array is too small to contain hills or valleys, such as arrays with fewer than 3 elements, or arrays that are entirely flat or monotonic, where the total count will always be 0. This approach is optimized by limiting our iteration to only the range where hills and valleys can form, specifically from the second element to the second to last element, avoiding unnecessary checks at the boundaries. For data structures, we use a list to store the preprocessed input with duplicates removed, and two integer counters, hill_count and valley_count, to track the counts efficiently. Analyzing the algorithm's complexity, we find that removing duplicates requires a single traversal of the array, which is O(n). Similarly, the iteration to detect hills and valleys is also O(n). Therefore, the overall time complexity is linear, O(n). In terms of space, the preprocessing creates a new list of size proportional to the input, resulting in a space complexity of O(n). This makes the solution both time and space efficient for the given problem. The implementation of the solution begins by removing consecutive duplicates from the input array. This ensures that the remaining elements are distinct and meaningful for comparison. Next, we initialize the hill and valley counters to 0. Then, we iterate through the array, checking the conditions for hills and valleys. If the value at the current index is greater than its neighbors, we increment the hill count. If it is smaller than its neighbors, we increment the valley count. Finally, after completing the iteration, we return the sum of these two counters. For example, if the input array is 2, 2, 3, 3, 3, 1, 1, the preprocessing step reduces it to 2, 3, 1. During the iteration, we find that the value 3 forms a hill because it is greater than both 2 and 1. Since there are no valleys in this example, the total count of hills and valleys is 1. To further illustrate, consider another input, 6, 6, 5, 5, 4, 4. After preprocessing, the array becomes 6, 5, 4. During the iteration, we evaluate the middle value, 5. Since 5 is smaller than both 6 and 4, it forms a valley. There are no hills in this case, so the total count is 1. This step-by-step process ensures we correctly identify and count hills and valleys in any valid input array, while handling edge cases and optimizing for efficiency. By following the outlined algorithm, we achieve an accurate and efficient solution to the problem. This solution to the problem count hills and valleys in an array begins by simplifying the input array. Consecutive duplicate values are redundant for determining hills or valleys, so they are removed. The simplified list is created by iterating through the input array nums and adding only unique consecutive values. For example, an array like 2, 2, 3, 3, 3, 4 is converted to 2, 3, 4. Next, we initialize a counter count to 0 to track the total number of hills and valleys. A hill is identified as a number that is greater than both its immediate neighbors, and a valley is identified as a number that is smaller than both its neighbors. The program iterates through the simplified array starting from the second element and ending at the second to last element, indices 1 to len, simplified, 2. This is because an element at the first or last position cannot have both left and right neighbors. For each element in this range, we check whether it forms a hill, greater than both neighbors, or a valley, smaller than both neighbors. If either condition is met, the counter is increment. Finally, the function returns the total count of hills and valleys. This approach ensures accurate results while maintaining a time complexity of O, n, where n is the length of the input array. The space complexity is also O, n, due to the creation of the simplified array. The solution handles edge cases such as arrays with all identical elements, arrays with no hills or valleys, and arrays of minimal length, e.g., length 1 or 2. Here, we begin by simplifying the input array to make it easier to process. The idea is to remove any consecutive duplicate values, as they don't contribute to identifying hills or valleys. To do this, we use a list called simplified, where we start by adding the first element of the array. Then, we iterate through the rest of the array, checking if the current value is different from the previous one. If it is, we add it to the simplified list. By the end of this loop, we have a condensed version of the input array containing only the distinct changes in elevation. Next, we initialize a counter called count to 0. This will keep track of the total number of hills and valleys we encounter. Now, to identify the hills and valleys, we iterate through the simplified list, starting from the second element and stopping before the last element, because the first and last elements cannot form hills or valleys on their own. For each element, we retrieve its previous, current, and next values from the list and then proceed to check their relative order. If the previous value is less than the current value and the current value is greater than the next value, we identify this as a hill and increment the count. Similarly, if the previous value is greater than the current value and the current value is less than the next value, we identify this as a valley and increment the count again. This way, we are able to count all the hills and valleys in the simplified list. Finally, after finishing the loop, we return the count, which represents the total number of hills and valleys in the array. This approach ensures that we only iterate through the array and the simplified list once, making the solution both efficient and easy to understand. To solve this problem, we start by simplifying the input array by removing consecutive duplicate elements. For the input 2, 4, 1, 1, 6, 5, we initialize the simplified array with the first element, 2. Then, we compare each subsequent element with the last element in the simplified array. If they differ, we append the element, otherwise, we skip it. For example, comparing 4 with 2, they are different, so we append 4, making the array 2, 4. Similarly, 1 is different from 4, so we append 1. When we compare the next one with the previous one, they are the same, so we skip it. Then, 6 is different from 1, so we append it, and finally, 5 is different from 6, so we append it. This process results in the final simplified array, 2, 4, 1, 6, 5, which we'll use for the next steps. Now that we have the simplified array 2, 4, 1, 6, 5, the next step is to count the hills and valleys. We initialize a counter, count, to 0 and iterate through the array, skipping the first and last elements since hills and valleys require both neighbors. At index 1, the value 4 has neighbors 2 and 1. Since 2, 4, 1, this forms a hill, so we increment the count to 1. At index 2, the value 1 has neighbors 4 and 6. Here, 4, 1, 6, which forms a valley, so we increment the count to 2. At index 3, the value 6 has neighbors 1 and 5. Since 1, 6, 5, this forms another hill, so we increment the count to 3. With no more elements to check, the final result is count equals 3. For the second example, the input array is 6, 6, 5, 5, 4, 1. We simplify it by starting with the first element, 6, and comparing each subsequent element with the last one in the simplified array. The second 6 matches the first, so we skip it. The next element, 5, differs from 6, so we append it, resulting in 6, 5. The next 5 matches the previous, so we skip it. Then, 4 differs from 5, so we append it, and finally, 1 differs from 4, so we append it. This gives us the simplified array, 6, 5, 4, 1. Moving to counting hills and valleys, we initialize count to 0. At index 1, the value 5 has neighbors 6 and 4. Since 6, 5, 4, this is neither a hill nor a valley. At index 2, the value 4 has neighbors 5 and 1. Again, 5, 4, 1 does not form a hill or valley. Therefore, the final count remains 0. In the third example, the input is 1, 2, 3, 4, 5. Simplifying this array starts with 1, and we compare each subsequent element with the last one in the simplified array. Since all elements are unique and in increasing order, each element is appended. Comparing 2 with 1, we append 2. Then, 3 differs from 2, so we append it, followed by 4 and 5. This results in the simplified array 1, 2, 3, 4, 5. Next, we count hills and valleys. We initialize count to 0 and check the middle elements. At index 1, the value 2 has neighbors 1 and 3. Since 1, 2, 3, it is neither a hill nor a valley. At index 2, the value 3 has neighbors 2 and 4. Again, 2, 3, 4 does not form a hill or valley. At index 3, the value 4 has neighbors 3 and 5. Similarly, 3, 4, 5 is neither a hill nor a valley. Thus, the final count remains 0. To summarize, after simplifying the input array and counting the hills and valleys for each example, the results are as follows. In the first example, the count is 3, representing 2 hills and 1 valley. In the second example, the count is 0, as no hills or valleys exist in the simplified array. Similarly, in the third example, the count remains 0, as the array represents a strictly increasing sequence with no hills or valleys. This approach ensures that we efficiently simplify the input and accurately count the hills and valleys in the array. In this problem, the time complexity of the solution is determined by 2 main computational steps. First, we simplify the input array nums by creating a new list called simplified, where consecutive duplicate values are removed. This step involves iterating through the entire nums array, which has a length of n, making this operation O, n. Next, we count the hills and valleys in the simplified array. To do this, we examine each element in simplified, excluding the first and last, and check if it satisfies the conditions for a hill or a valley. In the worst case, where all elements in nums are unique, the length of simplified is still at most n. Each check for a hill or valley involves constant time comparisons, and we traverse the array once, so this step is also O, n. Therefore, both steps contribute equally to the time complexity, making it O, n. Now, when we combine the 2 computational steps, the overall time complexity becomes O, n, plus O, n, which simplifies to O, n. For the space complexity, let's consider the memory usage. The input array nums itself does not contribute to additional space usage since it is provided as part of the problem. However, we do use the simplified array to store non-consecutive unique elements of nums. In the worst case, when all elements in nums are unique, the length of simplified will be equal to n, resulting in a space usage of O, n. Other variables, such as the counter count and the loop index I, require only a constant amount of space, or O, 1. Therefore, the overall space complexity of the solution is dominated by the simplified array, making it O(n). Let's compare this optimized solution with a brute force approach. A naive method would involve iterating through the array and directly checking for hills and valleys without removing consecutive duplicates. While this method still has a time complexity of O(n), it requires additional checks for consecutive duplicates during the hill or valley condition evaluations. This increases the number of redundant operations, making the constant factors in the time complexity higher. In contrast, the current optimized solution simplifies the array first, which eliminates unnecessary comparisons and ensures that the hill and valley checks are performed on a reduced size array. By avoiding redundant checks, the optimized solution is more efficient overall, even though both methods share the same O(n) time complexity in big O terms. Let's analyze the algorithm across the best, average, and worst cases. In the best case, where all elements in nums are identical, the simplified array will contain only one element. Although the simplification process still requires traversing the input array, the time complexity remains O(n). In the average case, the simplified array typically has fewer elements than nums, but the time complexity is still O(n), because both steps, simplification and counting, scale linearly with the size of the input. Finally, in the worst case, where all elements in nums are unique, the simplified array has the same length as nums. Despite this, the time complexity remains O(n), since the algorithm still involves two linear passes. Mathematically, the algorithm makes one pass through nums to construct simplified and another pass through simplified to count hills and valleys, resulting in O(n) plus O(n) equals O(n). Similarly, the space complexity is dominated by the simplified array, which has a maximum size of n, making it O(n). Thus, the solution is efficient in all scenarios. When solving this problem, there are a few common mistakes to watch out for. First, not ignoring consecutive duplicates in the array can lead to incorrect results. Consecutive duplicates, like the repeated 2s in 2, 2, 3, 2, don't contribute to hills or valleys. Skipping them ensures that only the unique pattern of neighbors is considered. Next, misinterpreting edge cases is another frequent issue. For example, arrays with fewer than 3 elements, such as an empty array or 1, 2, cannot have a hill or valley because there aren't enough elements to compare. Finally, incorrect boundary conditions can cause runtime errors. When comparing neighbors, you must ensure that both I1 and I+1 exist before accessing them. Forgetting this step might lead to out-of-bounds errors, which can crash your program. Another pitfall is overcomplicating the solution. Some people use nested loops or extra data structures, which significantly increase time complexity. A single pass through the array is all you need to solve this efficiently. Additionally, it's important to avoid counting the same hill or valley multiple times. This can happen if you don't have proper checks in place to ensure each hill or valley is only counted once, even if there are redundant elements nearby. From an interview perspective, this problem is about recognizing patterns. Hills and valleys are determined by comparing an element with its immediate neighbors, identifying local maxima and minima. The optimal approach involves a single pass and skipping duplicates, which ensures an O(n) time complexity. It's also good to discuss edge cases like single-element arrays, two-element arrays, or arrays where all elements are identical. Finally, be prepared to address follow-up questions, such as modifying your solution to count only hills or only valleys under certain constraints. This problem is closely related to several others on LeetCode that deal with identifying peaks or patterns in arrays. For example, problem number 852, peak index in a mountain array, and problem number 162, find peak element, both involve recognizing local maxima. Similarly, problem number 941, valid mountain array, and problem number 915, partition array into disjoint intervals, explore variations of array structure analysis. When considering alternative approaches, one option is the two-pointer method. This involves using 2 pointers to track the start and end of consecutive duplicates. While it minimizes redundant comparisons, it can be a bit more challenging to implement and debug. Another option is the brute force approach, where you compare every possible triplet of elements. While simple to understand, this results in an O(n)² time complexity, which becomes impractical for large arrays. The sliding window technique is another alternative worth mentioning. Here, you maintain a window of size 3 to analyze triplets of elements as you move through the array. While conceptually straightforward, managing the sliding window can introduce additional overhead, especially in how you update and maintain the window boundaries. Each of these approaches has its own trade-offs, so it's important to consider both the problem constraints and the input size when deciding which one to use. Thank you for joining today's session. To recap, we explored the problem of counting hills and valleys in an array, discussed the key algorithm, and highlighted important takeaways. Remember, mastering these types of problems strengthens your core problem-solving skills. If you found this helpful, please like, subscribe, and share. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!